Thank you. Basically, the goal of the talk is to explain a geometric method to some approach to some number theoretic problems. Okay, so let me start with the problem. Let's say X is a smooth and projective variety, and for the talk, I'm going to take this to be defined over the function field of a curve over a finite field. So B is a smooth projective curve. Then you have a variety defined over a non-algebraic closed field. The basic question is the set of rational points not empty? Okay. And of course, this is a very big problem, and in general, we don't expect any uniform answer. So today I'm going to focus on the so-called local global principle, or maybe Hasse principle, for this question. And the nice thing about this case is this is a function field of a curve, and we can really reduce this problem to some geometric problem over a finite field. Okay. Let's say I have X this is over this function field. Now this actually gives you a fibration. Okay. Pi. This is a flat projective family of varieties, so that the generic fiber, so I always use eta to denote the generic fiber of B, is actually isomorphic to X. Okay. And then we're interested in the case with, where you can find a rational point, and that's the same as sort of a map from the generic point to this family. Okay. And then, so here I have rational points. So by the evaluative criterion of properness, this gives you a section from B to the total family. Okay. So this is a section, so I have the composition with the projection is the identity on B. Okay. And conversely, if you have a section, you can always restrict the section to the generic point, so you recover the rational point. This is actually one-to-one. Okay. So then the question becomes, let's say you have a flat projective family over a curve. Okay, you find a section. Now there is a necessary condition for this. So if I have a section from B, X, this is the section. Now of course, for any closed point B, this is closed. Imply this. I can look at the completion of the local ring, and we call this the spectrum of the completion. Okay. So I can restrict the whole family to this completion. So I get X spec of this completion. Okay. Then if you have a section, of course, you can restrict the section to the spectrum. And that gives you a section, a formal section. So there is a formal section from spec of the completion to this family. Okay. I mean, if we're over the complex numbers, then you should think of this as like taking a really small disk around each point. And then this is saying that you have a section, then you should be able to find locally holomorphic sections around each point with sufficiently small neighborhood. Okay, now we say that the Hasse principle holds for this family pi if so this direction is true. In other words, this obvious necessary condition is also sufficient. This is, I mean, in general, for this global fields, the Hasse principle is formulated in terms of rational points and idyllic points. But if you unwrap all the definitions, this is equivalent to this form. Okay? And somehow in this talk, since I'm going to explain a geometric approach, this is going to be the definition I take. Okay. So then you can ask, so what is example of a variety so that the Hasse principle holds? So let me write it here. And this is really a classical theorem due to Hasse and Minkowski. So if X inside of Pn, this is a smooth quadric, then Hasse principle holds. Okay. This is the first example, and also this explains the name of Hasse principle. Okay. Then you can ask, what about other varieties? Can you find, other examples where Hasse principle holds? So the natural next step is to look at cubic hypersurfaces. And it turns out that for curves in P2, this Hasse, and also for cubic surfaces in P3, this Hasse principle fails. And there's a conjectural description or a conjectural explanation why the Hasse principle fails for cubic surfaces. And in general, if you have a, write it here. So if we expect that if X inside of Pn, this is a smooth final complete intersection. And also the dimension is at least 3. Then Hasse principle should hold. So for example, for cubics, you expect a cubic threefolds or maybe higher dimensional cubics, Hasse principle should hold. Okay. Maybe before I go into some results, let me say, why is this like a good criterion for checking rational points? I mean, essentially, to determine if you have a rational point, this is generally a difficult problem. But this Hasse principle, this criterion, is actually computable. Okay. So essentially, all you need to do is compute the fibers where this places where this fiber is singular, and and over is like defined with some finite field. So even a computer could check if you can find the formal section. Okay. So if you can prove Hasse principle holds, then this gives you a very good criterion to check the existence of a rational point. Okay. So then, in general, what do you know about what do we know about this final complete intersection? Even in the case when the dimension is at this 3, I think actually very little is known beyond this quadric case. Okay. So basically, what I can prove, maybe I'll just tell you, is that Hasse principle holds for, first of all, this is X inside of Pn, so the smooth cubic, and n is at least 5, and I have to assume that the characteristic is now 2, 3, or 5. Okay. So in other words, for cubic fourfolds are higher dimensional cubics, and also under this restriction on the characteristic, Hasse principle holds. And as I said, here you expect that actually Hasse principle holds for 3-dimensional cubics, but the proof cannot be pushed forward. You really cannot push the proof to prove that case. But on the other hand, there is another variety which is slightly simpler than this smooth cubic and slightly more complicated than quadric. So it's a complete intersection of 2 quadrics. So X inside of Pn, so the complete intersection of 2 quadrics. Okay. And here, indeed, you can prove what you expect. So n is at least 5. This is a 3-dimensional variety, and you have to assume the characteristic is now 2. Okay. I mean, so the proof of this theorem is really use this geometric approach. So you want to find a rational point in the moduli space of sections. Okay. And of course, so the advantage of this approach is that now you only need to find a rational point over a finite field. Okay. So finite field is much easier than this function field. But the disadvantage is now you have to work with the moduli space. So even if the variety is defined by some really explicit equation, this moduli space is quite complicated. And in general, there's no way to find equations of this moduli space. So what we need is to find some geometric properties which will actually give you a rational point. Okay. So this approach is really motivated by the theory of rational simple connectedness in characteristic zero. Okay. That's the theory developed by the Yuan star. Okay. But somehow, in characteristic P, there are several problems with their theory, and even if you want to apply their theory to these cases, the biggest difficulty is that they are not rationally simply connected. So you have to find out some replacement for their arguments. And today, so the main part of my talk is going to be a proof of this result, so the Hasse-Minkowski result, in the case when the characteristic is not 2. Okay, and this is a smooth quadric. Somehow I will try to present the proof in a way that you can actually understand what's going on for these two cases. Okay, and so some part of this proof is quite technical, but in the case of quadric surfaces, lots of technicalities just goes away. Okay, okay, so that's basically the plan of the talk. Maybe let me start with this board. So the first question you want to ask is, what kind of property will give you a rational point over a finite field? Okay. And for example, if you can prove that something is rationally connected, or maybe even rationally chain connected, then a result of it now actually tells you that there is a rational point. Okay. But I mean, this is essentially what the Yuan star are trying to do. They try, over in characteristic zero and over like function field of a curve, they try to prove that the moduli space of sections has like a canonically defined rationally connected subvariety, and then you produce a rational point. But somehow that's very technical. There are some parts of the argument which is very technical. And in our case, if you assume, for cubics and for complete intersection of two quadrics, and also quadrics, there is a reduction. So you only need to prove a very weak statement about the moduli space. So I want to first explain this. So it suffices to prove that there is a geometrically irreducible component. Let me call it sigma of the moduli space of sections. Okay. So this is the reduction. I mean, the moduli space of sections is defined over this finite field FQ, and it naturally breaks it up into like irreducible components. But some of them becomes reducible after you base change to FQ bar. Okay. So what I want is the irreducible component defined over FQ, which stays irreducible after you pass to FQ bar. Okay. That's what I mean. And let's prove this. So if we know this sigma exists, then by the Langway estimate, so by the Langway estimate, okay, so I know that sigma, it may not have a rational point over FQ, but it has a FQ to the n rational point whenever n is really large. So this n depends on sigma, of course. But once you fix the sigma, you can choose an n large enough that it has a rational point. Okay. And so for quadrics, there's a very nice property. So a quadric has a rational point if and only if it has a rational point after some odd degree field extension. Okay. So you can just choose this n to be a really large odd number. And then this tells you that there is a section over this field. So there's a rational point over the function field. Then by its property, this tells you that there's a rational point over the original function field. Okay. But somehow, for cubics and for complete intersection of two quadrics, at least I don't know any nice thing like this.
For intersection of two quadrics, it's true.
Oh, okay.
For intersection of two quadrics, it's true.
Okay, it's good to know. But still, I'm gonna continue with my plan. I'm gonna present a slightly different argument, okay, which also works for these two. So I'm gonna, of course, this is the same as saying that x has a fq to the n be rational point, right? It's not empty. Okay. For n really large. So the idea is to show that, okay, here x is actually a quadric, right? This is a smooth quadric. So I'm going to show that x, it has a rational point over degree 3 field extension, if and only if it has a rational point over the original field. Okay, this is not empty. It's not empty. Okay. I mean, if we admit this for the moment, then you can see that you can just make a sequence of field extensions, right? So you start with fq, then you go to fq to the third, and then fq to the ninth, and etc. Until you get a really large, finite field. Then you get a rational point, then you go back. Okay. So how do you see this? Well, just to see this, what you do is you take a rational point x, which is a rational point over this degree 3 field extension, and you take the Galois conjugate point, y and z, the Galois conjugate. And of course, if x is defined over the original field, then there's nothing to worry about. Then what you do is you consider the linear span. Let me write as this x, y, z of these 3 points inside of Pn. Okay. I mean, in general, given 3 points, you would expect that they span the P2. Okay. Of course, in the degenerate case, they span a line. But if they span a line, then you get this line would be also defined over FQB, okay, original field, and intersect the smooth quadric at 3 points. So this line has to lie in the smooth quadric. And of course, any line has a rational point, so you're okay. So if this is a P, so if this is a line, this is okay. And this is so if this is P2, P2 is also defined over the original field, then what you do is you take the intersection with x. So this is, well, of course, in the degenerate case, this P2 will be contained in x. Again, it's okay. So in the non-degenerate case, this is the conic. Okay. So conic is geometrically P1. Okay. But in this case, this is actually a P1 over this field because it has a degree 3 cycle. So x, y, z contained in this conic C. This conic. Okay. So any conic with a odd degree cycle is actually isomorphic to P1. Essentially, what you do is you take the dualizing sheaf, you tensor with this line bundle determined by this degree 3 cycle, that gives you O1, and you just take a section that gives you a rational point. The zero locus is a rational point. Okay, so this is the reduction, and somehow a similar argument works in these two cases as well. Okay, I mean, if you got bored at this point, you can just try to think about this. So what are the field excitation you have to take? Okay, so now this lemma reduces the proof to finding a geometrically irreducible component. Okay, then how do you do this? Well, to do this, we can so what I want to do is base change to FQ bar. Okay. So now we're over an algebraic closed field. And what I want to do is find an irreducible component, which is Galois invariant. So we want an irreducible component. This is over FQ bar, which is Galois invariant. So how do you do this? Well, maybe the first thing you want to ask yourself is whether there is actually any section over this FQ bar. You don't want to work with an empty space. And indeed, there are sections. So this is a classical theorem due to Chen and Lang, which actually tells you that there is a section. Implies that there is a section over F. Later, I will not write this FQ bar anymore, but from now on, everything is over an algebraic closed field. Okay. So somehow you want to start with this section and produce lots of irreducible components and ask whether one of them is Galois invariant. But somehow, for technical reasons, I don't want to start with an arbitrary section. I want to start with a nice section. Start with a nice section. Okay. So the condition of being nice essentially tells you that you can deform the section in any way you want. Okay. So this, in particular, this will be a smooth point in the moduli space. So the existence of a nice section is a non-trivial condition. Okay. So somehow you have to prove something about this quadric fibration over FQ bar. But I'm going to ignore those. At least, I mean, if you assume the total space you start with is smooth, then this is very easy. Okay. So the difficulty is when singularities arise, you have to worry about the section pass through singularities. So we start with the section S. And now everything, again, just to remind you, everything is over FQ bar. So I'm, let me see. Okay. No. You don't want, I mean, okay, so this is the subtle point. So you really want a family of quadric fibrations. You don't want to, you don't want to have like reducible fibers. And basically, if you have reducible fibers, then sections through different components, they are going to be, give you different irreducible components. You really don't want that. Okay, so this is the main construction. So far, I don't need that. But
the section is supposed to go. I mean, it hits only smooth points in the fibers everywhere.
You want that, but you have to prove that you can find.
Are you assuming that you have this? Or?
Yes, yes, that's yeah, that's part of the definition of being nice. Okay. Yeah. And I don't see why you need dimension at least 3 to get this.
No, but because you mentioned the fact that you wanted all the fibers to be reducible. That's why I was asking.
Actually, even in dimension 1 and 2, you can do that. I mean, okay. So I start with the next section, yeah. So in particular, this is the smooth point of the moduli space of sections. So I can take a unique irreducible component. I call it M0. This is the unique irreducible component containing this, the point represented by the section. Okay. Then what I'm going to do is, technically at this point, I should work with quadrics of dimension at least 3. Because I want to take a general line in a general fiber. So this is my section. I want to take a general line, okay, in a general fiber. And attach this to the section at some point. Okay. Again, as part of the definition of being nice, this is also a smooth point of some compactification of the moduli space of sections. So I can take M1 to be the unique irreducible component containing this. Okay. And you should also check that, so this section, indeed, you can smooth this nodal curve and you get an irreducible section. So a general point in M1 actually parameterizes a real section. Okay. There's something I have to check, but there are just deformation arguments. Now you can guess what I'm going to do next. So M2 is going to be the unique irreducible component containing this curve. Okay. Add 2 lines. Okay. And you continue. Okay. So you get infinitely many irreducible components of the space of sections. Now I want to ask a general question, which is not so much related to the talk, but I think this is somehow related to the theme of this special year. So what is the asymptotic behavior? Asymptotic behavior of this MI. So it's very easy to check that. So this, I make several choices. I should start with a section, and then add some lines. So it's very easy to see that this is independent of the line I choose. Okay, but it does depend on the section. Okay. So I want to ask. The question is, what is asymptotic behavior of this sequence? So the first question you want to ask is this independent of S, at least for I really large? Okay. So in some sense, if this is true, then it doesn't matter which section you start with. You get like a canonically defined sequence of space of sections. Then you can ask, what's the asymptotic behavior of this sequence? Okay. Asymptotic behavior. This MI. Now I can basically drop this S because this is sort of independent. Okay. And there are several questions you can ask, what do you mean by asymptotic behavior? So first of all, if you think about this Manning conjecture, this is really like saying that you've chosen a sequence of rational points, and then you can ask what's the asymptotic distribution of this rational point. Okay. So for example, if this is everything is defined over a finite field, you can ask, what's the number of sections? Okay, and is there any like asymptotic formula for that? But this argument that actually works over any, let's say, a perfect field. Okay, so you can ask, what's the limit in the sclerocentric ring of varieties? And even in a very simple case, where you just take the trivial product, you take a curve and take the product with x any variety, let's say rationally connected, so that you can really carry out this construction. The first question is no. So basically, this is saying that for each homology class, let's say this is over complex numbers. So the first question is asking, for each homology class, can you find a uniquely determined space of section? Space of rational curves. Because if this is a trivial product, then sections are the same as maps from the curve to this variety. Okay, and even if you take this curve to be rational, then this is still open. And in some very rare cases, for example, homogeneous space or maybe a toric variety, somehow you can actually show that there is a choice, and somehow there is a very nice asymptotic behavior in topology of this space of rational curves. Okay? Essentially, that tells you something about the topology of your variety X. Okay, so this. No, I mean so Gromf-Witten invariant, that would be a different question. What I'm thinking about is really it tells you the homotopy type of X. So this is somehow, if you consider, I'm lying a little bit, you have to consider pointed curve with the mark point to a fixed point in a variety, and somehow asymptotically, so it sort of converges or stabilizes to some loops, double loop space of your variety. Okay, so this is the general question, and for the purpose of this talk, the most relevant is this one, the first one. So if this Mi of S is independent of S, at least when I is really large, okay, then for each Mi, when I is really large, is Galois invariant. You shouldn't be surprised because you're sort of picking out the unique irreducible component. No. So how do you prove this? Well, if you know that there is a nice section where you base change to FQ bar, you know that there is a nice section. This S is defined over, say, FQ, some finite field extension. I think Q to the N over FQ. Okay, so you know that this section, this a priori is defined FQ bar, but it's actually defined over some finite field extension. And then you can take the Galois. Okay, then this implies that this Mi of S, okay, is defined over FQ to the N. Okay, so this whole sequence, they are defined over some finite field extension. Now, of course, you can take the Galois conjugate of this section S. So you take S1, S to the K, so these are Galois conjugates. Okay, of S. Of course, each of them gives you a sequence. But because this is, I assume that this sequence is independent of the section I choose. Okay, so you know that there is a really large number, and call this M, such as for any I is greater or equal to M, this Mi of Sj is really the same as Mi of Sj prime. Okay. So then, of course, you get Galois invariance. Okay. I mean, here this is really important that you first base change to a finite field extension. Basically, you think that you just work over FQ bar and you have to take like infinitely many sections, and then this number M could grow to infinity in some sense. So you have to work with the finite field extension. Okay. So this is the main construction, and if you can prove that this is sort of independent of the S, at least asymptotically, then you produce this irreducible section, irreducible component. Now this question becomes, how do you prove that these things essentially they're the same component, right? So basically what you need to show is that you can find a deformation from one section to the other section. Right? So if you can find a deformation parameterized by an irreducible curve, then you get this, they're the same. Okay. Unfortunately, so this is the part, why it doesn't work for cubic threefolds. The only way I know how to produce a deformation of two sections is to feed them into a ruled surface. And you think these two sections, you realize them as two sections of a ruled surface. And because this is a ruled surface, these two sections are rationally equivalent modulo fibers. Okay. Of course, a ruled surface fibers are rational curves, which roughly speaking gives you these lines and something more. And then, it's this lies in the rationally equivalent, so you can find the pencil inside this ruled surface. Okay. So what I want so let me draw this picture. Let's say I have a family, at some point we become singular. Okay. This is over the curve B. Okay. This is my total family. Now I have two sections. Okay. So this is S1, this is S2. Okay. So I want to find a ruled surface. So let me draw it here. This is the ruled surface. Some point again degenerates, so that you have again two sections, and called sigma 1 and sigma 2, and also a map that's over the curve B. Okay. So these are two sections, and if I can, and also sigma 1 is mapped to S1, this is mapped to S1, sigma 2 is mapped to S2. So if I can do this, then over the surface S, I will be able to find the pencil. So now if you look at the generic fiber of the picture, okay, so everything is over B. So if you look at the generic fiber of the picture, what I'm trying to do is, given two rational points, I will try to find a rational curve containing these two rational points, right? And of course, I have already told you how to do this. You take two rational points, and you take the third one. That gives you a P2, and you take the linear span, and that gives you a conic. Okay, so this will be the rational curve we're looking for. Okay, so this is actually the family of conics. So each of this is mapped to a conic. And of course, somehow it may degenerate, so you get two lines. Okay. And then I basically claim that if you do this very carefully, then you will not see a double line. Okay. So it's at worst like two lines. Okay. So in particular, every fiber is reduced. Okay. Then you take the sigma 1 plus some fibers. So this is rationally equivalent to sigma 2 plus fibers. Then you just take this pencil. Okay. Of course, here you have a conic, and here you add a line to this. Okay. So if you add a line, of course, this is okay, because by construction, you allow adding lines. Okay. But somehow, if you have to add a conic, then there's a little bit problem, because in the construction, you didn't add conics. But, so the solution to that is really you sort of deform this conic so it degenerates into two lines. Okay. And then you just, if you follow all these kind of constructions, you start with a section, and you add some maybe broken chain of lines, and then use this pencil, you deform one section to the other. Okay. So this is the general idea.
What is the equivalence taking place?
Over in S. The rational equivalent. Yeah. So this is the rough idea of the proof for this case of quadrics. And of course, I lied a little bit. So to get the independence of lines, you have to assume the quadric has dimension at least 3. Okay, because for quadric surfaces, you have 2 families of rulings. But I claim that's very easy to handle. Okay, and there's another point which I haven't explained. So in the whole proof so far, I didn't really mention the existence of local sections. Okay, because we're trying to prove that Hasse principle holds. So the assumption is that you have a section everywhere locally. And so far, if you think about the whole argument, it doesn't really use that much. Okay, and the reason is, first of all, this condition is most of the time this condition is satisfied. So it doesn't tell you anything new. Okay, and to explain how to actually use this condition, I want to give you 2 examples. And so in these examples, this condition really plays an important role. Okay. So example, let's consider 2 families over function field of P1. So x squared plus y squared plus t times c squared plus w squared equals to 0. And also xy plus t times c squared plus w squared equals to 0. I'm going to assume that so the square root of -1 is not in the base field. Okay. So with this assumption, you can see that the first equation has no solution. Okay. Essentially because it has no formal section at 0 when t equals to 0. And of course, the second one always have a solution. It doesn't matter what kind of hypothesis you put here. But if you base change to FQ bar, these 2 families will look the same. Okay, so essentially, when t is 0, you have this, and this is 0. You have a union of 2 hyperplanes, and the general fiber is a smooth quadric surface. Okay. So how does the existence of a section tells you how to differentiate these 2 families? Well, so if you have a section, which is, this is really saying that you have a formal section over FQ bar, which is Galois invariant. Okay. So let's assume it intersects one of these components and not at the common intersection. Okay. So of course, you look at the image of 0 inside of this. So it's very easy to show that this is a smooth point. So this is the smooth point, and that tells you that one of this irreducible component is actually defined over FQ. Right? And of course, this is a quadric, so the other one has to be defined over FQ too. Okay? So if you think about this argument, you start with the nice section, and you take the Galois conjugate. So the Galois conjugate of that section will all intersect this component. But if you don't have a section, so these 2 are Galois conjugate to each other, you start with a section, let's say like this. The Galois conjugate lies in here. Okay? And if you go through that argument very carefully, you will see that in this case, you still produce an irreducible component. And in this case, you will not, essentially because the Galois action will interchange these 2 components. Okay. But somehow this is a little bit ad hoc, because this is a quadric. So what do you do with cubic? What do you do with common intersection of 2 quadrics? Okay. So what I would actually want to do is the following. So you make a change of variable. Let's say x prime equals to t. X equals t times x prime. Y equals to y prime. Z equals to z prime. And w equals w prime for the second family. Now, if you think about this, you plug in everything, you get an actual factor t at the first one, right? The first monomial. Then, of course, this is over the function field. You can factorize this t. So what you get is x prime y prime plus z prime square plus w prime square equals to 0. So this family is the same as is isomorphic to that family. Okay? But somehow you can see that this is like a trivial fibration. Okay? In particular, the fiber over 0 is actually a smooth quadric surface. Okay. And of course, this is a very simple example. And in general, what you can do is, serves as a local model. Okay. In general, you can always perform this kind of operation, and it's kind of change of variable, so that you can make the central fiber at least like integral, okay, geometrically integral. Okay. So this is essentially an argument of Kolar. So in general, this also works for hypersurfaces, any degree. You can somehow find what he calls a semi-stable model. Of course, in general, if this is not a quadric or if it's a cubic, so the semi-stable model, you can still have like reducible fibers. Okay, that's still possible. But in the case of quadric and cubics, it's very easy to understand what sort of the degenerations of this family. Okay. So now this is basically the whole picture of the proof. You first apply Kolar's theory of semi-stable models, okay, and then you analyze, under the assumption that there's a formal section everywhere locally, you analyze what can appear in this degeneration. Okay? And then you find out they find very good. So everything is integral. Okay? And then you run this argument, and you have to be very careful about what's happening at these singular fibers. And because every quadric, you only have integral quadrics, and you take this, you're generally taking a intersection with P2 of some integral quadric to get a smooth conic. Okay. So in particular, for this family, over every point where this fibration is singular, you actually get a smooth quadric. Okay. Then when you look at this rational equivalence, you know that you don't have to add any fibers over the singular fibers. Okay. So then you basically avoid adding any rational curve in singular fibers, and that's good, because deformation theory is really difficult to understand for singular varieties. So you do everything very carefully, and you basically only need to deal with rational curves on smooth quadric hypersurfaces. Okay. So this is the general line of argument for quadric fibration. And of course, you can wonder what's happening for this cubic and the complete intersection of two quadrics. So first of all, that reduction, it still works. You only need to produce a geometrically irreducible component. And as a hint, so for cubic hypersurface, you can make degree 2 field extensions. And for complete intersection of two quadrics, you can make degree 3 field extensions. So the argument is basically the same. You take the linear span, then you look at the intersection, etc. Then this construction, of course, this works for any final complete intersection of index at least 2. So that's okay. Then it comes this part. Somehow you have to, given two rational points in this generic fiber, you have to be able to find a rational curve connecting them. So in particular, this tells you that the R equivalence is trivial. And this is known for complete intersection of two quadrics of dimension at least 3. Actually, this is known for all complete intersections of two quadrics of any, as long as this is rationally connected. Okay. But you can, from this proof, you can see that what you really need is a very explicit description of the rational curve. And fortunately, in the case of a dipedal surface of degree 4, the rational curve is very difficult to describe. So you don't have at least I don't have a very explicit description. Okay. For cubics, things are worse because we do not know that the R equivalence on a cubic threefold is trivial. But we do know that the R equivalence on a cubic fourfold is trivial. So this is the work of Madol. Actually, we have seen his name in the first lecture. Okay, so I think this is everything I want to cover. And I'm a little bit early, so we can have lunch. Okay, thank you.